Hi everyone, today I'll be explaining electric force and electric field. So first, what is an electric force? So this is the most general equation. It's Fe equals to K small q times big Q over R squared. It's very similar to the gravitational force equation. And K represents the Coulomb's constant, which you don't need to memorize it, but it's like just a constant. And it can also be sometimes written in this form. What's most important is that big Q signifies the source charge and small q signifies the point charge. So what I mean is that if we have a source here, and the charge is maybe like big Q, and if we have a point here, and this source is going to be affecting this point charge with a charge of small q plus or negative. Yeah. Just remember that because when we talk about electric fields, we're going to be using the source charge. So now for electric fields, the most basic equation is this one. And as we can deduce from our previous equation of electric force, electric field equals to K big Q over R squared. And this is only for like simple questions of like point charge questions, where we have a source and a point charge, and we want to find the electric field on these two objects. Yeah. So in this case, for electric field, we will always use big Q. That's the source charge. Yeah. Some important concepts to remember is that both the electric field and electric force are vectors, and they have the same direction. The direction of electric fields is always from a higher potential to a lower potential. And we'll talk about potential in like one of the next few classes. So for multiple charges, what I mean is that if there's one source charge, big Q, but there's multiple point charges, then we will use superposition. Some key concepts to remember is that if you're trying to find the electric force of the system, then you will deal with it in pairs, so pairs of forces. And if you want to find the electric fields of the system, you will deal with it separately, so each point charge. And just a little tip is always try to find symmetry in the system or in the shape. It will help you and simplify the problem a lot. So next, I'll be talking about field lines. Field lines are not the same thing as electric fields. There are lines that kind of represent the movement of electric fields. So some key concepts to remember is that it always goes from positive charge to negative charge. The electric field vector E is always tangent to the electric field lines. Line density, which is number of lines per unit area, is always proportional to the magnitude or the total electric field. And no field lines can cross each other. These two point kind of correlate because if the electric field vector E is tangent to the electric field lines, then since the electric field vectors should not cross, then the electric field lines can never cross because of the tangent electric field vectors. So the two most important basic graphs are these two. This is with a positive charge. All the field lines will be pointing inward towards the charge. And if like there's a negative charge, then its field lines will always be pointing outward. So I recommend you guys remember these two graphs. Yeah. And a further like use of those two graphs is with like when two opposite charges come together, they will attract. And when two like charges come together, they will repel. So in the first graph, you can see that it's two opposite charges and they will attract. However, you can also see that it goes from the positive charge to the negative charge. So I guess the field lines are kind of in this direction, as you can see from the arrows. However, the field lines over here, because we need to follow this law, you can see it's going inwards towards the negative charge. And these field lines over here go outwards, outwards of the positive charge. However, if you have two like charges, it doesn't need to be two positive charges. It could also be two negative charge. All the field lines will repel each other. So, yeah, so as you can tell, the field lines go outward, and also they don't move smoothly towards each other. They're repelling each other here. Yeah. So next, I will briefly talk about energy. Right now we use energy. Right now, when we talk about energy, we don't use the notation big E because that's the notation for electric field. It's a bit different from dynamics. However, still energy is a scalar value, therefore it only has a magnitude with no directions. And energy equals this formula, delta K plus U, where K represents the kinetic energy and U represents the potential energy. Potential energy for electric fields is different from like dynamics, and I'll talk about that in the later class. Yeah. So a special case is when energy is conserved. That's when delta K plus delta U equals to 0. Therefore, delta K equals to negative Q, and we get this formula. Here, how I went from delta U to delta V is delta U equals to Q times delta V. Delta U is electric potential, but delta U is electric potential energy, but delta V is only the potential. And there's like a slight difference here, and I'll talk about it in like a later class. Yeah. And just a reminder, this is a formula for kinetic energy. Lastly, I'll briefly talk about charge distribution, as it's very important to find the electric field of, not a point charge shape. And we use it a lot in Gauss's law, which I will talk about in the next class. So a charge distribution, the first three concepts is this. So this is for a linear case. Lambda equals to Q over L, and L, that's why it's linear. For area, tau equals to Q over A, this signifies the area. And for rho, and for volume, rho equals to Q over V, and this is a volume. So if we take the derivative on each side, we get these three formulas. We use this a lot in calculating electric field, as I said before, like this. So we know E equals to, I forgot K here, but KQ over R squared, right? So if we take the derivative on both sides, then that means dE equals to K dQ over R squared, and then take the integral on both sides. E equals to integral of K dQ over R squared. And we can substitute this dQ with these three formulas, which will significantly facilitate solving a problem. Yeah, so essentially what this is we're breaking we're breaking a shape into many small pieces, many small dQs, and solving them separately. So, and then at the end, summing it back together. And this will, make the problem, simplify the problem, and make it a lot easier to solve. Okay, that's all for a little introduction on electric force and electric field.